Hello everyone, today let's take a look at QP121, a pretty chill question. In front of you there's a basket with 2 red orbs and 1 blue orb, and then on each turn an orb is drawn at random and then replaced with a blue orb. So determine the expected number of draws required until all orbs are blue. So we have 2 red orbs and 1 blue orb. If we take out a blue orb, well then we're going to replace it with a blue orb, so we're going to be back in the exact same situation. And if we take out a red orb, then we're also going to replace it with a blue orb, so now we're going to be in this situation. Now once I'm in this state, if I draw one of the blue orbs, I'm going to replace it with a blue orb, but if I draw the red orb, well then I'm going to replace it with a blue orb. Now I have 3 blue orbs, so the game is over. So this is a question involving states. The easiest way to solve these is just to draw out a diagram first. So we start in the state when we have 1 blue orb and 2 red orbs, so I'm going to call that 1B. Now if I take out a blue orb, I'm going to replace it with another blue orb, so I'm going to be right back in the same situation. What's my probability of drawing the blue orb? Well, it's just going to be 1/3, obviously, so with 1/3 probability, I'm going to remain in this state. So I draw this arrow like so. Now instead, if I take out one of the red orbs with 2/3 probability, well then I'm going to be in the state where now I have 2 blue orbs. So I'm going to draw a 2B state right here, and I go to that state from this one with 2/3 probability. Now once I'm in the state with 2 blue orbs, if I draw a blue orb from this state, well then I'm going to replace it with another blue orb, so I'm going to be right back in the exact same situation. What's my probability of drawing a blue orb in this situation? Well, it's going to be 2/3 now, so I have an arrow here representing 2/3 probability. But instead, if I draw the red orb, well then I'm going to replace it with a blue orb, so now I'm going to be in a new state, and that's the state when I have 3 blue orbs. So I go to that state with 1/3 probability because I have a 1/3 chance of drawing a red ball in this state when I have 2 blue balls, right? And now once I'm in this state, the game is over. So we've drawn out our full diagram, and this is going to make it easier to think about. The question says that we start in the state when we have 2 red orbs and 1 blue orb. So we start right here, and it's asking us what is the expected number of draws that we need to get to this state over here when we have 3 blue orbs. Okay, so let me call T1 the expected number of flips from this state right here to get to this state. So we're trying to solve for this value here. Well, after my very first draw, I will have drawn 1 time. So we start with a 1. Now after I draw 1 time, I'll have a 1/3 probability of ending up in the exact same state that I started in, and a 2/3 probability of ending up in the state 2B. If I end up back in this state 1B with 1/3 probability, well then my expected number of flips is just going to be exactly the same as what it was right here. It's going to be T1 because we're in the same state that we started, right? Now the expected number of flips from this state, I'm going to have to introduce a new variable. I'm going to wind up there with 2/3 probability, and the expected number of flips from that state, I'm going to call T2. So my expected number of flips from this state is going to be 1 because we flipped, plus 1/3 T1 because we end up back in the exact same state with 1/3 probability, plus 2/3 T2 because we wind up in this state with 2/3 probability, and then we need to calculate the expected flips for that. And we can do pretty much the exact same thing for T2. So now let's find an equation for T2. Okay, so T2 represents the expected number of draws from this state right here to get to this one. So once I'm in the state with 2 blue balls, I do my draw. So we start with a 1 right here. Now after this draw, when I'm in that state, I'm going to have a 2/3 probability of winding up in the exact same state that I was. So plus 2/3 times T2. Then after that draw, I just have a 1/3 chance of actually ending up in my end state. So we don't have to add on anything for that. You could technically think about it like I'm adding on 1/3 times T3, where T3 is the expected number of flips to get to my end state, but the expected number of flips to get to my end state from this state is just going to be 0 because I'm already there, obviously, right? So we can just discount that. So now all I have to do is use these 2 equations and solve for T1. So first of all, T2, well, T2 is just going to be equal to, if we bring this to the other side, I have 1/3 times T2 equals 1, so T2 equals 3. T2 represents the expected number of draws that I have to do to get to my end state from this state over here where I have 2 blue balls, right? So now I can just plug that back into my equation up here. So when I do that, I get that T1 is equal to 1 plus 1/3 T1 plus 2/3 times 3, so just 2. So I rearrange this, I get 2/3 T1 is equal to 3. So when I multiply by 3 halves on both sides, I get that T1 is equal to 9 halves. So the expected number of draws from this state right here to reach my end state, the exact thing that we're trying to solve for, is 9 halves. I always think that this is the easiest way to think about it, but another way might be if you take the expected value of, let's say, B1 plus B2, where B1 here represents the number of draws to get to state 2, and B2 here represents the number of draws to get to state 3 from state 2. And then by linearity of expectation, you could break this up into the expected value of B1 plus the expected value of B2. And then the expected value of B1 we can basically model as a geometric with success probability 2/3. So the expected value of basically a geometric with success probability 2/3, well, we talked about that in QB 123, it's just going to be 1/2/3, so it's going to be equal to 3/2. Now for the expected value of B2, we're taking the expected number of draws from this state to get to this one, which again is going to be another geometric. This time our success probability is 1/3. A geometric represents the time until the first success, basically. So for the expected value of B2, it's just going to be the expected value of a geometric random variable with success probability 1/3, which is going to be 1 on 1/3, so 3. We derived those in QP 123. So now when we add these up right here, we have 3/2 plus 3. So that's going to be 9/2 as well. Yeah, so maybe this geometric way is a little bit easier to think about in this specific example, but when these get more complicated, these questions have more complicated diagrams. The diagram way is just going to be easier, in my opinion, to think about it.